I'm Jennifer Trelongo, and today we're going to be talking about porosity, permeability, and capillarity. I'll meet you inside. Okay guys, today we're going to be talking about porosity, permeability, and capillarity, as well as water retention. Capillarity and water retention are about the same thing, okay? So first thing we're going to look at is porosity. So I have unsorted sediment that's all mixed up. Look at all the silt, the sand, the pebbles, they're all mixed in there, okay? And then I also have straight up pebbles. These are sorted material, don't touch. Then I have sand, okay? That's sand and it's sorted. And then I have silt. And that's sorted as well, okay? So I just have a list here. Frankie, move. I just have a list here of exactly what is in each graduated cylinder. Okay, the first thing we're gonna look at is porosity. So that's the amount of pore space in each of these. So porosity, we talked about with SpongeBob being porous.
Who lives in a pineapple under the sea?
SpongeBob SquarePants!
Absorbent and yellow and porous is he.
SpongeBob SquarePants!
If nautical nonsense be something you wish,
SpongeBob SquarePants!
SpongeBob being porous. So something that is porous will hold water because it's got a lot of pore space, like this sponge. SpongeBob is porous, like they say in the theme song. Frankie, stop. You can't stop.
Take two.
Yeah. The next thing that we have is an egg from one of my chickens. This is not porous. It doesn't have any pore space in it. Like when I pull it out of the water, there's no water inside of it being held within the particles. So out of these three sediments, which one is more porous? And I ask you that all the time, but when you look at them, they're equal amounts, they're sorted. The porosity is actually equal on all of these. So if I poured water into the three of these, it would hold on to the same amount of water. There would be the same amount of water in the pore space.
I only know it.
Okay. And then there's unsorted sediment. Unsorted sediment would actually have a lower porosity because all the sand, the silt, the clay, it fills in all the little pore spaces. Okay, the next thing we look at is permeability. So permeability is water seeping downward through this sediment. So if you watch, I'll start with this one. Okay, I'm trying to do blue. You could see it slowly seeping downward. Okay, slowly seeping. This one's even faster. Super fast, right? It's amazing. It's shocking. So this one has a low permeability. This one has a high permeability. Okay, so permeability increases when the sediment size increases. The last thing we look at is capillarity. So capillarity, I have a picture of that for you.
As you can see, you have silt on the left, followed by sand in the middle, and then pebbles on the right. And if you place the tubes upside down with an opening at the bottom, the blue water will seep up through the silt much, much higher. So that means that it has a greater capillarity. Whereas the pebbles the water doesn't really seep up as high.
Okay, the last part of this is water retention. So, what sediment holds on to the most water? And we did this in class, but I poured all that water, that blue water, into the pebbles, and you can see pebbles does not hold on to a lot of water. Okay, there's really not any water retention there. Okay, it's almost cleared out of all the water. Sand holds on to a little bit more than pebbles, but I mean, it still doesn't have the lowest water retention. Silt, I can't get any sediment, or I can't get any water out of the silt. This has the highest water retention out of pebbles, sand, and silt. And it's because it's the smaller sediment. Smaller sediment has a greater water retention, a greater capillarity. Okay? So you can see the difference between the three sediments. So there'll be 5 problematic questions to answer about this lesson. Good luck.
Bound to erupt. Krakatoa!